This is one of the most important sections in the whole course. I personally think it's the most interesting section in all of calculus. This is section 11.10. It's called Taylor and Maclaurin Series. Okay, so we have been working with, we've been finding power series representations of various functions in the last section. However, they all require the use of a formula that we already knew. But we don't want to be limited to that. We want to be able to find a power series representation for any function. So our new question in this section is if a function has a power series representation, what is it? Okay, so let's answer this question. So suppose f of x has a power series representation centered at A. And so what that means is that f of x is equal to c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and it goes on. Let me actually write one more here, plus c4 times x minus a to the fourth. This does go on forever, but we're going to develop a pattern right now, so I'm going to write down the first several, okay? So question, of course, is how do we find, so our goal is to find all these coefficients. Find the CIs. So how do we do this? So we need a trick. How can we get rid of all of these terms except for the one that we're looking for? So the way that we do this is by plugging things in. So what I'm going to do is I'm going to take the center and plug it in. So what would f of a be? Well, I want you to think about what happens when you plug x equals a into this, right? Don't all the terms go away except for the constant term? We end up getting this. And so c naught is f of a. This is our first discovery. So what we end up with saying is that if we want to know what the first coefficient is of our power series, all we have to do is plug a into the original function. But we are now stuck because how would we find C1? We can't plug anything else in that's going to work, right? So here's the trick. The trick is to take the derivative. So what would f prime of x be as a series? Remember, we know what happens when you plug in f prime of x. We know how to take the derivative of a series. You just differentiate term by term. So the c naught goes away. We're going to end up with c1 plus power rule 2c2 times x minus a plus 3c3 times x minus a squared plus 4c4 times x minus a cubed plus. And now that we've made everything go down by 1 degree, we can find C1 by plugging in x equals a again, except now we're plugging it into the derivative. So what is f prime of a equal to? Well, when you plug in x equals a, everything here goes away, and you're just left with C1. So we get that C1 is equal to f prime of a. So we're starting to see a pattern here, except we're not sure if this pattern is going to continue. We're going to do this a couple more times until we get the pattern for sure, okay? So what I'm going to do now is take another derivative, f double prime of x. The c1 is going to go away, but now we're just left with 2c2, and everything else goes down by a power. Notice that this 2 comes down and multiplies by the 3, so we end up with plus 3 times 2. I'm going to leave it like that, 3 times 2, C3 times x minus a, plus 4 times 3, C4 times x minus a squared, plus, and we go on, right? So if we plug in x equals a into this, let's see what we get. This time we don't get C2 directly, we just end up with 2C2, right? So what does C2 equal if we solve for C2 in that relationship? We get f double prime of a divided by 2. Now I'm going to insert something here which might seem a little random, but, well, actually let me wait, because the next term that we find will really sink the pattern, or will really help this pattern sink in, okay? So we're going to take another derivative. I'm going to do the third derivative here. I'm going to write a little 3 up here. Remember, that's another symbol that means take derivatives 3 times. If we take the derivative, we're going to end up with 3 times 2 times C3 plus, here we get 4 times 3 times 2 times x minus a plus, and then we got more stuff, right? So what would the third derivative of a equal? Everything goes away except for 3 times 2 times C3, or if we solve for C3, we get C3 is equal to the third derivative evaluated at a divided by 3 times 2, right? What is 3 times 2? Isn't that 3 factorial? And isn't the one above really 2 factorial? And you notice that the next term is going to give me this 4 times 3 times 2, which is really 4 factorial. So the point of me doing this was to illustrate a pattern that we're seeing. The pattern is that if we want any Cn, we can do that by using the following formula. So let's write this down. This means that Cn is equal to the nth derivative at a divided by n factorial. So again, for consistency, if we define 0 factorial to equal 1 and the 0th derivative of a function to just be the function itself, then the formula holds for all n. So this formula right here is the key. So if we go back, do you notice that this can be thought of as the f of a could really be thought of as the 0th derivative of a divided by 0 factorial, right? Because, 0th derivative we just defined to be just the function, and 0 factorial is just 1, right? And this is f prime of a over 1 factorial. So you could see that the pattern actually starts from the very, very beginning. So we now know the power series representation. So theorem. If a power series representation exists for a function f centered at a, then it is that formula right there where Cn is equal to that. Okay? In other words, these guys are the coefficients. So if we were to write this all out, so another way I could write this, so i.e. f of x is equal to, another way we could write this with one single formula is just to take the Cn's and replace it. It looks like this. So that's what we get. And how would we write this out in terms of, so let me write this out in the next line. So expanding, this becomes, you could take a function and always write it this way. The first guy is going to be f of a plus, and then we get f prime of a times x minus a. And then we get f double prime of a over 2 factorial times x minus a squared plus, and then we get the third derivative at a divided by 3 factorial times x minus a cubed. And this is the pattern. It goes on and on forever. Okay, so this is what all of this means. This is the theorem. We call this formula the Taylor series of f of x centered at a. The Taylor series of f of x centered at a. Sometimes I like to abbreviate this as Taylor series centered at a of f of x. Okay, so, this is just another way of writing that entire sentence. So in general, you can choose any center that you want as long as the function is defined there. We can center it anywhere, and so the most common place to center a series is at 0. So the most common place to center a Taylor series is 0. Okay, what that means is we end up with the following formula. So this is the Taylor series centered at 0 of f of x. Remember, this is just going to be the formula nth derivative at 0 divided by n factorial, and then it just becomes x to the n, right? Because remember, it's x minus a to the n, but a is 0. This is the same as if we were to write out all these terms, it looks like this. F of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus f third derivative at 0 divided by 3 factorial times x cubed. There you go. Okay, this is so common that we give it a special name. So we call the Taylor series of f of x centered at 0 the Maclaurin series of f of x. Okay, so Maclaurin series is just a fancy name that means the Taylor series with center 0 of the function, okay? So what I like to do is just call it Maclaurin series of f of x. And remember, this is the same as the Taylor series centered at 0 of f of x, okay? These two mean the exact same thing. So what are the steps then in order to find this thing? Because it remains that we need to be able to figure out a pattern of the derivatives, right? Because we can't take derivatives forever. So here are the steps. So steps for finding the Taylor series centered at A of f of x, okay? So step 1 is going to be to find f of A, f prime of A, f double prime of A, and just keep doing this until we find a pattern. Slash formula for the nth derivative at A. Okay, usually, the problems that we give you to work out, there will be a pattern that is, readily available. You're not going to have to think too hard to see that pattern, hopefully. Okay? And that's it, right? Once you find this pattern, then step 2 is you just write your answer. Your answer will always be, you take whatever you found for that pattern and you put it into this summation formula, right? So this guy is just going to become the numerator of your fraction. And if the problem asks you to find the Taylor or Maclaurin series, and it also asks you to find the radius of convergence, you can, just like we learned in previous sections, you can use the ratio test to find its radius of convergence. Okay? All right, so let's go ahead and do some examples. So example 1. Find the Maclaurin series for f of x equals e to the x and its radius of convergence. Okay, and you'll notice that there is no way to relate this to 1 over 1 minus x like we did in the previous section, right? So this is why we need to use this new formula to do this. So we want to find the Maclaurin series for f of x is equal to e to the x, okay? So remember I said we need to take derivatives here. What we're looking for then, remember the Maclaurin series, these words, is the same as the Taylor series centered at 0 for the function e to the x, okay? This is what we're trying to do. So what I like to do to find a pattern of derivatives is I like to create what I call a derivative table, okay? So here's how you do it. Create an n, create this, and then create this column, okay? So the idea is that for each n, we're going to calculate this, okay? Now look, we know that the Taylor series formula is equal to the following thing, right? We know that this is equal to the nth derivative at 0 over n factorial times x to the n. And so what we're looking for here is a pattern for this numerator, so we know what to put in the sigma, okay? So that's what we're working on right now. So here's how we do it. Start your table, start with n equals 0, which of course the 0th derivative is just the function e to the x, and then we plug in 0 because that's the center that we're interested in. So if you plug in 0, you get e to the 0, which is 1. Okay, let's keep going here. If I plug in n equals 1, that means we now take a first derivative. So the derivative of e to the x is e to the x, and then plug in 0, we get 1. Is this going to keep happening? Or are we just going to keep getting 1? Well, let's try it one more time. If we plug in a 2, another derivative, isn't it true that no matter how many derivatives we take, the derivative is, or the function is not going to change? So that means when you plug in 0, you're going to get 1 every time. So the pattern is easy. When you get a general n, you get the same guy, and so we know we're just going to get 1. So this guy right here, this is what we want, right? This is the nth derivative, and so a 1 is what we're going to put as this numerator. And so what does this mean? The Maclaurin series for e to the x is equal to 1 over n factorial times x to the n. So this is e to the x. This is another way of writing e to the x. Pretty neat, right? We found a way to take e to the x and write it as a formula, right? As a power series. So the question, though, is what is the radius of convergence of this thing? These aren't very useful unless it's got a big radius of convergence. Otherwise, we know it's not going to be accurate everywhere, right? So what would the radius of convergence, the radius of convergence be? So what we're going to do is we're going to use the ratio test on that. So we're going to do the limit as n goes to infinity of the absolute value of, remember you plug in the n plus first term, so you get x to the n plus 1 over n plus 1 factorial, and then you do the reciprocal. This is going to become n factorial over x to the n, and cancel x to the n with on top, you just have a 1x left. And so I'm going to start writing that here. That pulls out of the limit. I get an absolute value of x outside. And what do I have left for the limit? I'm doing the limit as n goes to infinity of, I just have an n plus 1 on the bottom left, right? And of course, if I send this guy to infinity, this actually goes to 0, right? This guy goes to 0. And so we end up with 0, which is less than 1 everywhere. So what does this mean? This means that the radius of convergence is infinity for this Taylor series, or the Maclaurin series, right? Which means that this formula is valid for any x that you plug in. It's pretty cool, right? If you want to know a useful thing that this could be done, what this means is that if you were to plug in 1 into that formula, then this means that you could find a way to approximate e on your own, right? Because e is the same as e to the first power, which is the same as, if you plug in a 1 into that formula, all the x to the n's go away. You just get this, right? 1 over n factorial. So you just get 1 plus 1 plus 1/2 plus 1/6 plus, and that will give you e. Pretty interesting, right? That's not part of our solution to this problem. This is just me showing you something cool that you can do with this information. Now, this is a very famous formula in math. I mean, I would recommend memorizing this just because it comes up in future math classes. It's a good thing to know. But just so you know, we can find the Taylor series centered at anything. So as another practice problem, how about we'll find a Taylor series of e to the x centered somewhere else. So let's find the Taylor series for e to the x centered at 2. In other words, we're looking for the Taylor series centered at 2 of the function e to the x. Remember, we can automatically write this down. We know that this is going to be, because of our formula, it's the nth derivative at 2 divided by n factorial, and then we're going to have x minus 2 to the n's there. Okay, but of course, we need to make our derivative table so that we can try to figure out our pattern here, okay? So I'm going to do a derivative table just like the one I did here. So I'm going to have n, and then fn of x, and then we're going to plug in 2, right? So fn of 2. So starting with n equals 0. Yeah. Starting with n equals 0. Okay? So what do we get for n equals 0? Well, we're going to take a derivative, or sorry, we're not going to take a derivative, it's just the function, e to the x, except now we're going to plug 2 in, so we just get e squared. Now for n equals 1, that means we take a derivative. This becomes e to the x, and then we get e squared again. And you notice this is going to keep happening, right? Every derivative of e to the x never changes, so if we go to the nth space, we know that we're going to get e squared for that one. And so e squared right here becomes our numerator of this fraction. And so our answer ends up being e squared over n factorial times x minus 2 to the n. So this is my Taylor series centered at 2 for e to the x. If we were to write down the terms, this is what these look like, right? Plugging in n equals 0, our first term is just e squared plus. Our next term is e squared times x minus 2. Our next term is e squared over 2 factorial, so over 2 times x minus 2 squared, plus our next term would be e squared over 3 factorial, which is 6, times x minus 2 cubed, and we could just keep going. So this is e to the x just as much as this one is e to the x, okay? They both equal e to the x. The only difference is the center of the Taylor series, right? This one had center 0. The other one has center 2. In the long run, though, when you go to infinity and you do this forever, it equals the function everywhere, not just at the center. But I will say that in general, Maclaurin series of f of x is used to approximate values of x near 0. The Taylor series centered at a of f of x is used for values of, I shouldn't say values of x, let me change that, it should be values of f of x. With x near a. Okay, What I mean by near zero is I mean the input values. Okay, so as long as you're trying to find, if you're trying to approximate, for example, e to the power of 0.01, I can use the Taylor series formula centered at 0 because I won't need to go out that many terms in order for the series to give me a close value. This is kind of jumping ahead a little bit, though. I wouldn't worry too much about that. Just worry about finding these Taylor series. Now, it's worth noting here, even though the problem didn't ask us to do the radius of convergence, if we had calculated it using the ratio test, we actually would have got a radius of convergence at infinity. So we would have got the same thing. Okay. Okay, those two examples were fun, but I hope you see that this was extremely simple, right? Because the derivatives never change. In other words, we're getting a constant for the numerator because the derivative doesn't matter, right? It doesn't matter how many derivatives we take, that value never changes. But I want to do a more complicated example so that we could see that it's not always this easy to find the nth derivative at a. So let's do another example. This will be number 3. I want us to find, this time I'll use the notation, I want us to find the Maclaurin series of sine of x. Okay. Now, sine is a much more complicated function than e to the x, right? The derivatives always change. And so we're going to see that this one is not so simple. But remember, this is the same as asking for the Taylor series centered at 0 of sine of x. Okay. So what is the Maclaurin series of sine of x as far as writing our formula down? Remember, we know it's going to be the nth derivative at 0 divided by n factorial times x to the n. But we do need to figure out what this top guy is, right? We're going to need to figure that out by doing our table. So let's go ahead and do that. We have our table here. I'm going to write nth derivative at 0 and nth derivative, oh sorry, that should say x before. Nth derivative at x and nth derivative at 0. So let's see what happens, okay? So if we plug in n equals 0 first. So that's just the function, so I'm going to put sine of x here, right? So if we plug 0 in, we get 0. Okay, so far so good. Let's try another one. If we plug in n equals 1, this means take a derivative, right? So we take a derivative, we get cosine of x. So we plug in 0, we get 1. Okay, we don't quite see a pattern yet, so we have to keep going. What if we plug in 2? For n, that means we're taking a second derivative, so take a derivative, again, we get negative sine of x. If we plug in 0, we get 0. Now I'm going to put 3. This means take a third derivative. So the derivative of negative sine x is negative cosine x. Plug in 0, we get negative 1. We still don't see a pattern, but let me show you what happens when we take one more derivative. The derivative of negative cosine x is just positive sine x, and so we get 0, and I hope you notice something, that we have just repeated the pattern, right? Because this went back to sine, this means that we're really just going into a cycle of 4 different answers, right? We're alternating between 0, 1, 0, negative 1, right? So how would we write such a pattern down? It's not easy to write a pattern down when something is alternating by zeros. However, I'm going to show you how to do that, okay? The trick here is that we can't really do it as a function of n, but we're going to re-index our variable so that we only count the ones that appear. So here's what I mean by that, okay? Let's first write out what this formula is altogether, okay? So here's what we get. We get our first term is 0, of course, so it's just going to be 0. And let me go ahead and actually write out the whole thing. So that's our first one. Next we get 1. Then we get another 0. Then we get a minus 1. Then this pattern repeats. So let me just write out a few more. Now, we could go on and on forever, right? So the pattern is 0, 1, 0, negative 1, and you'll see that I put that pattern in all my numerators here. Okay, but watch what happens. Anything with a 0 is gone, right? So there's no point in even writing it down. These are all gone. What am I left with? The trick is to notice that the only thing that we're left with are odd powers, right? Look, the first term is x to the first, and the factorial matches, right? X to the first over 1 factorial. X cubed over 3 factorial. X to the 5th over 5 factorial. X to the 7th over 7 factorial. So let me write this down. Only odd powers remain, so we reindex. Let me show you what I mean by that, okay? So how would we write this pattern, right? What's left is the following. 1 over 1 factorial x to the first minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. So this is our pattern, right? So let's go ahead and turn that into sigma notation here. So notice I cannot tell the sigma to count up by 2. So what I do is I still start at n equals 0 to infinity, right? Now here's the trick though. The trick is the fact that 2n is always an even number and 2n plus 1 is always an odd number, right? So really what's happening is we have the following. We have a 2n plus 1 factorial on the bottom and an x to the 2n plus 1. This is guaranteeing that we only get the odd powers of x and also the same odd factorials, right? I hope you're not confused at why the denominator needed a 2n plus 1 also. That's because this number matches that. This number matches that, right? The factorial has to match the power. There are only odd factorials, right? Now, what do I put for my numerator? Well, at this point, you notice that there's an alternating 1 or negative 1 on the top, right? Anytime we have an alternating 1 to negative 1, this is going to be negative 1 to the power of either n or n minus 1, depending on whether we started with a positive or not. Notice that we started with a positive, okay? So what that means is I need to put negative 1 to the n. Only because starting with n equals 0, we want to make sure that our first term is positive and not negative, right? So we're done. This is our series. What does this mean, guys? This means that sine of x is equal to that. So if we were to write down just in long form what we just showed, so this means that another way of writing sine of x as a series is we start off with, let's see, the first one would be just x plus, the next one would be, let's see, 1 over 3 factorial, so that's Oh, and that would be a minus, right? So minus 1/6 x cubed plus, and then it's going to be 1 over 5 factorial. What's 5 factorial? 120, right? 24, 120. So it would be plus 1 over 120 x to the 5th. And we can continue that pattern forever, but this is sine of x. It's just another way of writing sine of x. Okay. This is if you wanted to write it without sigma notation, but of course with sigma notation, it's nice and compact. I just wanted you guys to have an idea of what we were looking at. So, I'm going to do another example. Okay? However, I want us to note something. Note, we can still use term by term differentiation to help us go from a Taylor series to, for example, a Taylor series of a derivative, as long as the center doesn't change. Okay, let me show you what I mean. Okay, we're going to do another example, except instead of having to do it from scratch, we're going to be able to use the problem that we just did. Okay, so for our fourth example, I want us to find the Maclaurin series of cosine of x. Now, could we do it the way that we just did, right? Where we just list every single derivative and find the pattern? Yes, of course. We can do the exact same thing we just did. However, there is a faster way of doing this, okay? The faster way is to notice that the derivative of sine is cosine, right? So we know that the derivative of sine of x is equal to cosine of x, right? So doesn't that mean that I could just take the derivative of the series for sine that I found in my last problem to get the series for cosine? Yes, this is what it means, okay? Because we're looking for the Maclaurin series of both, so that means we're looking at the same center. Otherwise, the polynomials wouldn't match up because they wouldn't have the same center. But because we want a center of 0, this is not going to change the center. So let's go ahead and take a derivative of this. So what would we get? Well, remember, we can just use term by term differentiation. So we're going to use the power rule on this. So you bring the exponent of x down. And so what do we get? This doesn't change. And this guy doesn't change. And so we brought down the 2n plus 1. And so we're left with x to the, you subtract 1 from the power, you get 2n. But what's 2n plus 1 over 2n plus 1 factorial? Remember, 2n plus 1 factorial, another way of writing that is 2n plus 1 times 2n factorial. So we can cancel the 2n plus 1 with the 2n plus 1. And what are we left with for cosine? We're left with this. Okay. So interestingly enough, cosine has only even powers and factorials left, and sine has only odd powers and factorials left. Okay? So how would you remember this? So here's an easy way to remember that this one's cosine and this one is sine. This makes sense if you think of the nature of the functions, right? You notice that sine is an odd function and cosine is an even function. We're sort of understanding now why the words even and odd have been used for this type of function. It's because their Taylor series or their Maclaurin series has only odd and or even powers, right? So the odd function sine is the one with all the odd powers only, and the even function cosine is the one with all the even powers and factorials only. Okay? By the way, even though we didn't show it, it's not hard to show that both of these guys have a radius of convergence of infinity, just like e to the x. You just use the ratio test on it and you can practice. Okay. Now, this was a neat trick, right? It was cool that we didn't have to do cosine from scratch. I'm going to keep teaching you guys some manipulation tricks, okay? So let's go over another trick. If we multiply Taylor series by x minus a to any power, it is still a Taylor series centered at a. Okay. Also, plugging in x minus a to any power you want into f keeps the Taylor series intact also. Okay? So we can use this to find a Taylor series from a known one. Without having to start from scratch. And so I'm going to illustrate this with another example. So this will be problem 5. I want us to find the Maclaurin series for x squared cosine x. Yeah, x squared cosine x. Now, you can imagine that based on how hard cosine was to do, if we had done it from scratch, x squared cosine x would be a pretty tricky problem if we were doing it from scratch. Okay, however, let me show you a nice trick based on what I mentioned in the last part, okay? We know that cosine of x is equal to the following series, right? We had negative 1 to the n over 2n factorial x to the 2n, right? So if we were to multiply it by x squared, that means we just have to multiply this series by x squared. So how would we actually multiply that by x squared? Well, we can put the x squared into the sigma and then just add 2 to the exponent of the x. And so we end up with we end up with this. This is super cool because we do not have to do anything from scratch. All we did is we used simple algebra. We can basically treat these things like polynomials. Okay, so this is a really cool consequence of these results. I want to do another one. This one's going to be trickier, okay? So let me do this from scratch on the next page here. I want us to find the Taylor series centered at pi over 6 of sine of x. Okay, this one's trickier because plugging in 0 the last time made a lot of the terms go away. But let's see what we actually get here, okay? I'm going to do my derivative table, as you guys know, right? I have my n, I have my fn of x, and then I have my fn at pi over 6. Okay, so let's start with n equals 0. N equals 0, which is of course my sine of x. And so if I plug pi over 6 into there, I get a half. Now let's take a derivative. If I actually take a derivative of sine, I get cosine of x. And if I plug in pi over 6 into cosine, I know that cosine of pi over 6 is root 3 over 2. Then if I plug in 2 for n, that means take a derivative. I get negative sine of x, which is negative a half. And then if I plug in 3, I get negative cosine of x, which is negative root 3 over 2. And if I go again, we notice that this becomes sine of x, and so the pattern just repeats. And so this went right back to the top, right? So I know that I'm going to have these guys repeating forever. So instead of the last one, when I did sine and we had zeros every other term and they disappeared, we do not have zeros for this one. How do we deal with that? Okay, so the trick is to realize that the even powers, these are the even powers, right? And all of those are going to have the halves, and then the odd powers are going to have these. Okay, so the even powers have the root 3 over, the 1/2, and the negative 1/2 just alternating, and the other guys are going to have the root 3 over 2s. So actually what we're going to have to do is split it up into two different series, okay? So let's start with the evens. So I get 1/2 over 0 factorial x to the 0. I'm going to use two different colors here to show you the different powers. The next one, remember, is plus root 3 over 2 over 1 factorial x to the first. And then to go back to my evens, I have minus 1/2 over 2 factorial x squared. And then I have plus, minus root 3 over 2 over 3 factorial x cubed. And so this is the pattern, right? So let's do all of the evens as one series and all the odds of the other series, okay? So we do actually need to write it as two different series. So what are the evens going to give us? Okay, well, I know that I have a fraction. I know that I have a 1/2, so you know what I'll do is I'll write it like this. So let me erase a little bit here. Let me write it like this. I have 1/2. And then I know I'm going to have alternating signs. And for the evens, I know that I have a 2n factorial x to the 2n, and I'm starting off with a positive, and so this would be an n right here. And so these are my even terms. What are my odd terms? My odd terms are root 3 over 2 times, I know I'm alternating, and the first odd term is positive, so it's also -1 to the n, and then I have a 2n plus 1 factorial x to the 2n plus 1. So the red guys are the evens, and the green guys are the odds, and so the answer is going to be the sum of the two series, okay? I have to add together these two series, okay? So I need to do this guy plus this guy. This is going to give me all the terms, isn't it? So unfortunately, sometimes there's only one way to write a series. This is the way that you write it. We actually need two different series to write this series because there's no pattern that works for both, right? The patterns are different. One alternates between 1/2 and -1/2. The others alternate between root 3 over 2 and negative root 3 over 2. So this is the only way to write it down. Okay, so we could see that not centering at 0 can result in some tricky answers. I want to do one more important series. It's going to require a little bit of work here. So this is number 7. I want us to find, so let me actually start by fixing. So fix a real number. Okay. I want us to find the Maclaurin series for 1 plus x to the k. So I want to find the Maclaurin series for 1 plus x to the k. So this is going to require some development here, but we're going to see that this is really cool because this will allow us to take any binomial, which is two terms raised to a power, and we're going to be able to write that as a power series, or a Maclaurin series in this case. Okay, so let's just write down our derivative table and see if we can get to the answer here, okay? So remember, we're going to put n, and then fn of x, and then fn of 0. You know what? I'm going to need a little bit more room for this one. Let me do that right here. And fn of x, and then fn of 0. Let's see what happens. So let's start with, so let me write down, we know that we're going to have this, right? Oh, it's just centered at 0, I apologize. So it's x to the n, right? And so what we're trying to do is find this numerator here. Okay, so let's see what we get. For n equals 0, it's just the function, which is 1 plus x to the k. And so if we plug in 0 into that, we just get 1 plus 1 to the k, which is just 1. Okay, so now let's take a derivative. If we take a derivative of this, we get k times 1 plus x to the k minus 1. And if you plug in 0 into this, we get k. How about the next one? If we take another derivative, we actually get k times k minus 1 times 1 plus x to the k minus 2. So if we plug in x equals 0 into this, we get k times k minus 1. So I'm hoping we could see the pattern here. The third one is going to be k times k minus 1 times k minus 2. What we're doing is just going down that many terms from k. So what would the nth one be? Well, if you think about it, we need to go down n times. So it's going to be k minus 1, k minus 2, all the way until not k minus n, but it's actually k minus n plus 1, right? Because we started at k minus 0. Just like on n equals 3, we went down to k minus 2, not k minus 3. Yikes. Okay, so that means that we need to take all of this and make that my numerator up here, okay? So we have gotten our answer. Our answer is k minus 1, all the way to k minus n plus 1, divided by n factorial x to the n. Okay. Now, there is a nice way to write this, okay? This is such a famous series in math that we actually came up, or mathematicians came up with a nice notation for this term right here. So definition, we have something called k choose n. Or a way that your calculator has this, it might say this on your calculator, KCN. This is all the same, okay? What this means is exactly that guy that's in the box up there. K minus 1, all the way to k minus n plus 1, divided by n factorial. What this means is that we can rewrite our series with this nice compact notation, which is k choose n, x to the n. This is how we write that. Okay? So this is the exact way that we derive this series. And now we can actually apply this formula anytime that we want. Okay? So let's do an example. Let's do a simple one and then we'll do a tricky one, okay? So this will be number 8. I want us to find the Maclaurin series for 1 plus x to the 7th. Oh, you know what? Let me make it a nice small number. How about 2? Maclaurin series for 1 plus x to the 2nd. Okay, so remember, we already have a formula for this. In this case, k is 2, right? And so this is going to be, we're just going to write 2 choose n, and then x to the n. And let's actually write these terms out, okay? The first term is going to be 2 choose 0. By the way, just so you guys are aware, k choose 0 is always defined to be 1. So we get 2 choose 0 plus 2 choose 1 x plus 2 choose 2 x squared plus 2 choose 3 x cubed plus, and then this goes on, right? So what is 2 choose 0? That's of course 1. What's 2 choose 1? Well, that would be 2 over 1 factorial x. And what's 2 choose 2? This is 2 times 1 over 2 factorial times x squared. What's 2 choose 3? This is 2 times 1 times 0 over 3 factorial x cubed, right? But let's actually expand. Isn't this 1 plus, this is 2x, and then this would be x squared. But I want you to see what happens here. This term has a 0 in it, doesn't it? So this guy is actually gone. But wait a minute, all of them are going to have zeros after. So they're all gone. So actually we just get this. Interesting, isn't it? Our series is really just what happens when you multiply 1 plus x squared out. That's right. If something is already a polynomial, then its Taylor series is really just the function itself, right? Because all the other coefficients are going to be 0 in the polynomial. Cool. In many ways, what I just did is sort of check the formula, right? And it does work. But let's do something more interesting, okay? What we're going to do is we're going to apply this to, let's do something interesting. How about we do 1 plus x to the 1/2 power? Pretty weird, right? This is actually the square root of 1 plus x, but we're going to use the same formula, okay? Because now k is just a half. And so this is going to equal 1/2 choose n, x to the n. So this is going to be 1/2 choose 0 plus 1/2 choose 1 x plus 1/2 choose 2 x squared plus 1/2 choose 3 x cubed plus, it goes on forever. Now look guys, this is the answer, but I want you to be aware of what those symbols mean. So let's at least calculate these first 4 terms so that you understand what the terms are, okay? First term is just going to be 1 because it's choose 0. The next term is going to be 1/2, right? What's this guy going to be? So this guy is 1/2 times, you subtract 1, right? So it's negative 1/2, and then divided by 2 factorial. So what would that be? That would be negative 1/8, right? So it would be negative 1/8 x squared. What would the next guy be? This would be 1/2 times negative 1/2 times negative 3/2, right? We keep subtracting 1. How many times? The bottom is going to be 3 factorial, which is 6. So what would this give us? This is 3 over 8 times 6. This would give us 3 over 48, which is 1 over 16. And so we get 1 over 16 x cubed. And the pattern continues. There's no nice way of writing these numbers, but this is the pattern if we calculate the first 4 terms. Now notice this will never hit 0, right? We skipped over 0 because this thing is not a polynomial, right? This guy is not a polynomial. So of course, there's no way that its Taylor series can be a polynomial, right? It's got to go on forever. Let me do one more example to show you that you don't even need a 1 to be there in this problem, or even an x. So this will be a tricky one. This is number 10. I want us to find the Maclaurin series for the function 1 over the cube root of 5 minus 3x. So the cube root of, 1 over the cube root of 5 minus 3x is the same as 5 minus 3x to the negative 1/3 power. The trick here is to pull out a 5 because we do need this guy, we need to turn it into a 1. So the way we're going to do that is actually by pulling out a 5 to the negative 1/3 power. If we pull that out, we end up with a 1 minus a 3/5 x to the negative 1/3 power. So the trick then is now we can use the formula with this guy, except we're also replacing, if I write a plus here and then a negative here, what we're doing is we're replacing x in our formula with that, and then this is our k. So this becomes our x in the formula, and that becomes our k. And so here's what we get. We get that this function is the same as, I'm going to put the 5 to the negative 1/3 on the outside, and then we've got our series, and then we've got our k, choose n, and then we've got negative 3/5 x to the nth power. So this is what we get. Or if I want to write this out, I get the following. This is, so let's actually expand what's inside, okay? And then I'll put the 5 in at the very end, okay? So we end up with negative 1/3, choose n, and then we get negative 1. I'll take that guy out, and then I have a 3 to the n, and then I have a 5 to the n, and then I have an x to the n. But now I can put that 5 in, and that 5 to the negative 1/3 means it's going to get added to the bottom. And so my formula becomes the following. Okay, it's complicated, but that is our answer. And if we wanted to, we could write out the first few terms like in the last example. But you could see that this is a very powerful formula because we took something that didn't even look like a binomial, and after rewriting it with a negative exponent here and then pulling out the 5 to the negative 1/3 to get that 1 there, we were able to use the formula 1 plus x to the k on it. Okay, so to summarize, guys, a table of all important Maclaurin series we've derived in the last few sections are on page 768 in our textbook, Stewart, 8th edition. Okay, you don't need to memorize this table, but everything that we've written down can be found there as far as the Maclaurin series, okay? The functions that are on that table are things like sine, cosine, 1 over 1 minus x, e to the x, and so on, okay? I want to do one last example, okay? Can we use this method to find an unknown non-elementary antiderivative? The answer is yes. Okay, so as our last example, I believe the last one we did is 10, so this will be example 11. I want us to find the integral of e to the x squared dx as a series. Okay, so you may or may not know this, but the integral, let me actually make it, just to make it more interesting, how about we make it e to the negative x squared? You may or may not know this, but the integral e to the negative x squared, just as an antiderivative, you cannot write this without a series, okay? It's impossible to integrate this. So here's the trick then. We know that e to the x is the same as x to the n over n factorial, right? That is our Maclaurin series that we already derived. It was our very first example in this video, okay? So what we're going to do now is just replace the x in here, right? Before it was an x, now we're going to replace it with negative x squared in the formula, right? And so we end up with negative x squared to the n over n factorial, all right? And remember, we're about to anti-differentiate this, so we had better split it up. It goes like this, negative 1 to the n, x to the 2n, because that's x squared, over n factorial. So this guy right here is e to the negative x squared. So if we want to take the integral of e to the negative x squared, all we have to do is take the integral of that series, and we know that's really easy to do. So I'm going to put the plus c first. And then remember, you add 1 and then divide by that power. So it's going to be 2n plus 1. And so this is going to be our answer. There you go. Isn't that neat? We were able to take an antiderivative. And I know that this may not seem like we really did it, like it seems like we cheated, but this is just as valid. This is an antiderivative for the other series, and you can use this to do a variety of things with antiderivatives, like solve differential equations or other interesting stuff that you'll learn if you keep going on in math. Okay, guys, I hope you found this video useful. My favorite section in all of calculus. Thank you very much for watching.